In example 3, we have a great manufacturing application. We have an open box being constructed from a single sheet metal piece that is 18 inches by 30 inches. And the way that we're going to construct it is by cutting squares that are all the same size from the four corners and then bending up the remaining sides. So here is a sketch of what this would look like. So we start with our sheet metal, we snip out corners with a standard dimension, and then we take the remaining sides that are left and we fold them upwards. And so then we can then solder or weld the edges and we have our metal box. But we want to do this in such a way that we get the largest possible volume for the given area of sheet metal. So they want us to figure out how big the square should be that we snip out, and they want us to figure out what is the volume. Well, here's what I'm going to do. So it's not really convenient for me to sketch on this one and drag it back and forth. So let me make a quick sketch of our sheet metal that we can refer to, and then we can set up our problem. Okay, so here's our sketch, and we know that the total length is going to be 30 inches, and we know the total width is 18 inches. Okay, so let's do this. I don't know what the length of the square should be, so let me call that x. So this is x, and since it's a square, the length and the width are equal, so these are also going to be x's. And so I can now talk about how long this side would be that gets folded up. And that's what I'm going to be left with when I cut this out. And remember that when I'm trying to maximize the volume of the box. Well, volume is equal to length times width times height. And when I fold these edges up, x actually becomes my height. So it's going to be important for me to think about the other two dimensions, length and width, in terms of this amount x that is being removed. So if this total length is 18, and I'm snipping out an x on this side and on this side, that means that what I'm going to be left with is 18 minus 2x. And likewise, along this side, the total length is 30, but we're removing an x here and an x here, so that leaves us with 30 minus 2x. So now we can find our volume as a function of x. And that's going to be length times width times height. So the length is 30 minus 2x times the width, which is 18 minus 2x, times the height, which is x. And then you can FOIL these two binomials and distribute the x, and we end up with a cubic. And it's actually going to be 4x cubed minus 96x squared plus 540x. And remember, it's the volume that we want to maximize, and so the volume is what we need to differentiate. So we'll take the first derivative with respect to x, and we get 3 times 4 is 12x squared minus 2 times 92. 2 times 96 is 192, x plus 540. And now we want to set this equal to 0 to find our critical values. And we can factor out a 12. That leaves us with x squared minus 16x plus 45. And you can probably see very quickly that once we divide out the 12, this is not something that's going to factor with rational roots. So you can use the quadratic formula or some other method. I'm actually just going to complete the square real quick. So x squared minus 16x plus blank is equal to, and we move the 45 over to the other side, so negative 45 plus blank. And so to complete the square, we take half of 16 and we square it. So half of 16 is 8, so we get 8 squared. And then minus 45 plus 8 squared. 8 squared is 64, so I'll just rewrite that as 64. Now on the left side, this is going to factor as a difference of squares. And that's on purpose. We knew that was going to happen. That's why we added the 8 squared, the half of this. This is basically your difference of squares formula. And then on the right-hand side, negative 45 plus 64 gives us 19. And if we take the square root, we get x minus 8 is equal to plus or minus the square root of 19. And x is equal to 8 plus or minus the square root of 19. Now, one thing that we didn't talk about is the domain for our function v. So, and actually, I need to, instead of v, I need to think about x, the domain for x. So the smallest that x could be would be 0. So the domain for x, that would be not cutting out anything. So that's less than x is less than, and what would be the biggest x that I could cut out? Well, if this is 18 wide, since 18 is the smaller of the two dimensions, half of 18 would be 9. So that means that x can never be larger than 9. So if you look at these two values here, I want to check both of them and see if they're both in the domain for x. So what we find out is that x equals 8 plus the square root of 19 is actually about 12.4. And so for that reason, we're going to discard that one. But x equals 8 minus the square root of 19 is approximately 3.641 using 3 decimal places. So now we can find the volume by taking that value, 3.641. So that's going to be the side length that we need to cut out. And if we plug this value back into our volume formula, we can calculate our volume, and that's going to give us approximately 886.5 cubic inches. And so that is a maximized volume. That's the largest possible volume we can get from this sheet of metal by folding it into a box.